Hi there. Thanks again for joining us. This is Space Nuts, a Q&A edition. My name is Andrew Dunkley, your host. It's good to have your company. A Q&A edition means that people ask us questions and we don't do anything about it, except try to answer them. Justin has sent a question in about planetary orbits versus energy. He doesn't quite get what's going on there. Larry is asking about whether or not the Earth is expanding in relation to the universe expanding. Giles wants to talk about solid metal projectiles in a what-if question. And Mike wants to talk about nothing.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And back to share his wealth of knowledge with us is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. That's a nice word, is wealth, isn't it?
Wealth, yes.
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 That knowledge is fine, but doesn't make you wealthy.
No, it doesn't, does it?
No.
Does not, unless you know what to use it for.
Yes, that's right. Yeah. Could be.
Yes. Never mind. Let's get some questions sorted out because we've got a batch of really, really good ones again today. And our first question comes from Justin.
Hello, Fred and Andrew. It's Justin down in Melbourne. Thank you for answering my first question earlier this year. I have another question now which relates to the solar system. We're told that classical physics can't explain the existence of the atom because negatively charged particles orbiting a positive nucleus would lose energy and spiral in towards a nucleus. And of course, we need quantum mechanics to explain the atom's stability. But by extension, I was thinking about the solar system. How is it that the planets maintain orbits around the sun without losing energy and spiraling in towards the sun? If you think about that classic demonstration with the rubber sheet and the bowling ball with some marbles, the marbles will orbit the bowling ball, but then very quickly lose energy and find themselves next to the bowling ball. And of course, that's due to the friction of the rubber sheet. But I'm assuming there's a frictional component even in interplanetary space. But is it the fact that that really is negligible even on geological timescales and wouldn't cause the planets to lose energy? So perhaps you can walk us through how that works. And my second question is to do with the fact that the planets themselves obviously gravitationally interact, and perhaps there are some resonances there as well, which can cause planets to move either closer or further away from the sun, as Jupiter is supposed to have done in its lifespan. So given that the sun is at the halfway point in its life, do we foresee any radical restructuring or reshuffling of the planets in the solar system in the sun's second half of life? I love the podcast, and I hope you can share some insights on that one. Thank you.
We will do our very best. Actually, I won't do anything. Thank you, Justin. I'll hand it all over to Fred. So 2 questions, really interesting, both of them. Planetary orbits versus energy. Why don't they sort of slow down and fall in like you do with the old bowling ball on a rubber mat trick? And the planets reshuffling as the sun gets older. So we'll do them separately. It's a good question. I don't know if we've had this one recently. We might have had it before, but what keeps them keeping on, Fred?
Well, they do. They just keep on keeping on. So Justin's right in that, yes, the thing that sends the marble down to the bowling ball on the rubber sheet is the friction of the rolling phenomenon. All sorts of frictions come in. There's a bit of air braking as well with that, not much, but and that's what leads to that situation. In the solar system, there's very little to provide any kind of friction, if at all. The outward pressure of the solar wind is, in terms of planetary dynamics, exerts a negligible force. That the force actually does affect small objects like asteroids. We've discussed recently how the sun's radiation can speed up the spin of asteroids. That's an effect whose name I can't remember, but that's the case. So it's essentially a situation where you've set these things in motion, and the speed of rotation determines or revolution determines how far away they are from the sun. We are in a very stable era in the solar system, notwithstanding the fact that it seems counterintuitive that they should just be able to go on forever, rotating in their orbits, to sort of lurch towards the second part of Justin's question. Yes, there probably have been migrations, we believe, of planets from one orbit to another. Things are very, very stable as they are now, incredibly stable.
Good. It's good.
We have, and probably for the second half of the sun's life, things will remain much as they are now. The moon's drifting away from the Earth. We know about that. That's because it's losing energy, or gaining energy from the slowdown of the Earth's rotation. That pushes it further and further out. But in terms of the planets, there isn't anything really similar going on. The sun's mass is by far the biggest component, by a huge amount, of the mass of the solar system. And Jupiter's mass is by a huge amount the biggest component of the mass of the planets. So Jupiter certainly calls the shots, and that's why we've got an asteroid belt where we have, because Jupiter's gravitational interaction with the debris disk from which the planet's formed probably sort of stymied the idea of things sticking together well there. As soon as protoplanets stuck together, or as planetesimals stuck together, they got blasted apart by the gravitational pull of Jupiter, and probably collisions as well. The history of the solar system is probably dominated in its early era by planetary orbits evolving, and that's just because the density of material, there's still a lot of debris left in the dust disk. There's a lot of collisions taking place, and perhaps some gravitational instabilities that just needed to get themselves sorted out. Justin mentioned resonances, and there are many situations like that in the solar system. There's a group of asteroids called the Hilda asteroids, which are in the main asteroid belt, but they have a resonance with Jupiter. So for every 3 orbits of a Hilda asteroid, you get 2 orbits of Jupiter. So every 3 of Hilda and 2 of Jupiter, they find.
Yes, we talked about this before.
Place.
And didn't we find some weird exoplanet that had like 8 planets?
Yes, that's right. Yes, that's right. There is one. I think that's the TRAPPIST. I think it's one of the TRAPPIST planetary systems. Yes, and they're all in neat orders because they're all in resonance. And that's something that's evolved, probably quite early on in the history of that planetary system. You've got this array of planets that do pull themselves into resonant orbits. Now, there aren't really resonances between the planets, except that Pluto is in resonance with Neptune. I can't remember, that might be 3-2 as well. For every 3 orbits of Neptune, 2 of Pluto. You might need to check what those numbers are, but it is a resonance. It's called a resonant object. And so that's come about over time. Neptune is much more dominant than Pluto in its gravitational pull. Yeah. So
it is it's a 3-2 resonance.
3-2. Okay. Yeah. So that's a fairly common one. So yes, it does happen. But the way things are now is they're very stable. They've evolved over 4.7 billion years, and they're pretty happy with the way things are, I think.
Yeah, it's fascinating, isn't it? You mentioned that effect of the sun on asteroids. There's actually 2 effects. There's the Yorp effect, which that's the spin rate.
4 names, 4 people.
Yeah, and the Yarkovsky effect, which is where the sun heats the asteroid up, which causes it to emit heat, which acts as a tiny thruster, which accelerates its orbital speed.
Yeah, but these are the tiny bodies of the solar system, so their orbits are evolving, as that suggests. But very much they're not planets.
No, definitely not. So there's basically nothing stopping the planets from just doing what they're doing forever until the sun gives up and says, all right, I've had enough of you lot, and gets too big for itself.
That's right.
Yes. So nothing to worry about, Justin. You can go to work tomorrow. Oh, I heard him say. Thanks for the question, Justin. Lovely to hear from you. Our next question comes from Larry. I know we've been down this road before, actually, but it's a great question. Larry asks, if space is expanding, then is the Earth also expanding? By how much, and would it be measurable? Now, I seem to remember a conversation we had a long time ago about the fact that as the universe expands, everything is expanding with it and moving further and further away, and we're going to reach a point where it will expand so much that we won't be able to see anything because everything will be just too far away for the light to reach us. But I think I did ask you the question as to whether or not my next-door neighbour's house will be moving away from me, and the answer was yes, wasn't it?
No, it's no.
It's no, right. Yeah.
You're stuck with them, I'm afraid.
Damn.
Yeah. So you're right that the space occupied by the Earth is expanding, but it's it's not even microscopic. It's at a subatomic level over even geological lifetimes, probably, because it's such a small distance. The universe is very, very big. And
you might think it's a long way to the
exactly,
down the road
yes,
to the chemist.
Chemist shop, yeah. That's twice we've had Douglas Adams in.
It is.
Yeah.
They're worth quoting.
Yes. In recent weeks, I was going to say, yes, they are worth quoting. So it's you only really see the expansion when you start looking out millions of light years. Then you do, as Hubble discovered back in 1929. But the reason why the Earth is not participating in that expansion is that the forces that hold atoms together and that holds the Earth together, which is certainly gravity in terms of keeping the Earth together, is by far the dominant force. So the Earth's self-gravity is easily enough to basically to overcome any tendency of the space within which the Earth sits to expand. It's micro. On the scale of the solar system, you can forget the cosmic expansion.
Right.
In fact, on the scale of our galaxy, you can forget it, basically.
Okay.
It's only when you start looking at more distant galaxies that you start seeing any measurable velocity change.
Okay.
So yep, gravity overcomes all.
Yes, it does. So, sorry, Larry, you're stuck with your neighbours as I am with mine. It's just the way it is. Earth will hold itself together. We are tough. Good question, though. Good question. I was going to say, yeah, if you do want to send us questions, you can do so on our website, and I'll tell you about that at the end of the show. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
The crew of Artemis II now bound for the moon. Humanity's next great voyage begins.
Space Nuts.
Our next question, Fred, is going to be a quick one because basically it's about nothing.
This is Mike from Cromer in the UK. You had a question, on the podcast I'm listening to, about beginning of the universe, as in the Big Bang. You referred to it as being nothing before it. Surely, from a non-science point of view, it would be better to say there was something before the Big Bang, but you don't know what it was. Why do you refer to it as nothing before the Big Bang? Bit of a strange question, but I thought I'd ask. Cheers.
Thank you, Mike. I think it was me that said that we thought there was nothing before the Big Bang, and I think your answer was no, it wasn't nothing. It's we don't know. Is that right, or am I getting crossed up with something else?
No, but I mean that's right as well. The issue, yes. So the standard line is. In the beginning, there was nothing, and then it exploded. Yes. That's that's a standard line, and that's very glib. The issue I have with trying to explain this is not with the word nothing, or even with the word something, which is what Mike would prefer, something, but we don't know what it was. But the issue I have is with the word before, because our understanding of the universe, certainly as far as relativity informs us, the models that you can build, time started with the Big Bang. Now that is the prevalent theory, but it is only one theory. There are others that do suggest that there was something before the Big Bang. Roger Penrose is one of the proponents of that sort of thing. But the kind of classical relativistic theory of the origin of the universe is that it's not that there was nothing before the Big Bang. It's that there was no time, and so before is not defined. Before has no meaning. Before only has meaning if you're in a time domain, and time, the start of the universe maybe created time as well as space, and that sort of ties in with some of the theories that are upcoming now, from which you and I have talked about. The idea that time is an illusion, really is an illusion, that emerges from a much deeper level. By quantum entanglement. That's the thinking. I'm not clear in my own head how these things link together. But it's certainly a very interesting possibility. And so that, the idea that before the Big Bang, that there was no before the Big Bang, because time didn't exist then, that would seem to be a possibility, given that we're looking for a deeper theory that explains the existence of the universe, in which time is not really a player. Time comes up as an illusion rather than a real thing. It's fascinating stuff. A lot of it's as Mike says, it's almost into philosophy rather than science. But the scientists are working hard on it. I'm really interested in this stuff because I think Einstein himself was convinced that time's an illusion, and he wrote something to that effect to a widow of one of his best friends who just died. It said time is a no, it wasn't. He said the idea of past, present, and future is a stubbornly persistent illusion. That was those were his words in his letter.
Yeah, I've read a theory a while back that suggested that all of time overlaps and that everything we know exists simultaneously.
Yeah. That's what comes out of relativity. That's the Einstein view, exactly. That and it comes from the fact that we realized very shortly after after Einstein developed his special theory of relativity in 1905, there was a mathematician who kind of unpicked the details, and it was from there that we realized that time is actually a dimension which behaves a little bit like space, because you can bend time. Relativity bends time. And that's one of the things that tells you that it's probably not a very deep and fundamental thing. And so Einstein's view of the universe was exactly what you've just elucidated. The idea that everything, past, present, and future, all exist in some way, and our sort of gradual progress through them from past to future is the bit that's an illusion. It has a name that is called the block time theory of the universe. It's sort of time is in a single block, if I can put it that way, and we just step through it from moment to moment, but it all exists.
Yeah. There's another element to that which we've also talked about before, and that is that our existence is a manifestation of our own. What our lives are, what our world is, what our planet, what our universe is a manifestation of ours. I don't know how they come to that concept, but that's another theory that's been put forward, that none of this is real. We've just created it in our collective minds.
Yeah, which tells you that a consciousness might be a fundamental part of the universe.
Yeah.
And if it took the universe several billion years to evolve creatures that had consciousness, what was happening before that?
Maybe we just live in a giant mind.
We just made it all up. Yeah.
Or a big black hole. That's another theory
Well,
too.
that's another, yeah. But thanks for that, Mike. It's good to try and get these things sorted out in our heads. And Cromer's quite a nice part of the world, if I remember rightly. I've never been to the Isle of Wight, but that's where it is.
Wonderful. Thank you, Mike. Very thought-provoking. We love those kinds of questions.
3, 2, 1.
Space nuts.
Our final question today comes from Giles. This is really interesting as well. This is a what if. Hi from England, Andrew and Fred. A popular idea in science fiction when dealing with objects in fixed orbits, such as space stations or planetary targets, is simply to fire big rocks at them from a ship elsewhere in the system. What sort of accuracy could we currently hope to achieve with a simple shaped solid metal projectile fired from low Earth orbit, dropping through the atmosphere, assuming no corrective adjustments after launch? Could we, for instance, landscape London, or would we be lucky to hit something in the vicinity of England? I assume hitting a target in orbit would be much easier to achieve. Giles. Now, before you answer this, Fred, it's really interesting that he brings that up, because I am currently reading a John Birmingham series called World War 3.2. And it's called, subtitled The Axis of Time. John Birmingham's from the UK, but he's living in Australia up in Queensland. I love his writing.
Once did a gig with him.
Yeah, he's a lovely guy, and he writes beautifully. I love his books. Highly recommend them if you're into science fiction. And in this series, there were 3 books, and he enjoyed writing them so much, he wrote 3 more books, which were just novelettes. And then he announced, look, I'm going to keep going. This is just too much fun. And he's written 3 more books, and he's now announced he's going to keep going again on this series.
Good on him.
It's got some great characters in it, including Prince Harry, who's actually one of the main characters of the story. You've got to remember that Prince Harry was thrust back in time to World War II with the rest of a fleet and so on and so forth. So there's time travel in it, all that. But what's interesting is in those novelettes in between, they were trying to rescue a scientist, a rocket scientist or a nuclear scientist to try and stop Russia from getting a nuclear weapon, and et cetera, et cetera. As a part of that, Stalin decides to lash out against the Allies in Europe and attacks them with tungsten spears fired from a weapons platform in orbit and obliterates the NATO forces. So that's exactly what Giles is talking about.
Yeah.
And they, even though it's not a nuclear weapon, the effect, from what John writes in his novels, the effect is the same.
It probably was. Yeah. I mean, it's just hurling things down, whether it's got explosive in it or not.
No, they didn't.
Down from
not
orbital
in this
speed.
case.
That's right. You've got enough momentum in order to, when you convert that to energy, in order to make a big impact, which is why we lost the dinosaurs back in the day.
Same thing.
Explosion from that. So I think Giles's question is how well you could control that.
Yes.
And he's right in that from, firing an object from orbit from one place to another is straightforward, because the dominant feature there is the interaction of the object with gravity, and it's there's gravity generally in the solar system from the sun and the planets, and that's highly predictable. And of course, we had a dead-on bullseye hit with the DART spacecraft on Dimorphos back in 2022. That I can't remember, it was within just a few meters of the target, and that's because it's easy to do that with high precision. I guess when you're putting something down to the Earth's surface from orbit, you've got the vagaries of the atmosphere to deal with, and so you've got winds which are probably having some influence at different levels. You're still talking about very high velocities, though, so they would, for your descending object, the winds would have some effect, but maybe not as much as you would think. We're now entering an era of hypersonic missile technology, which could be launched from orbit. And those things are very high-speed vehicles that can be steered in atmosphere. That's why they're different from ballistic missiles, which follow just the laws of gravity and a bit of atmospheric interaction. So you can kind of work out where they're going to land or where they're going to come in and intercept them. With defensive missiles, that doesn't hold true for hypersonics because they can steer to get out of the way. I don't know why I thought of that, but it's just this business of how you target something. The atmosphere is going to make a difference.
Yeah, I imagine it would. But what Joseph Stalin did to overcome that problem was saturation bombing.
Yeah.
From space with tungsten spears. So it didn't matter if he...
This is in the book.
This is in the book,
history.
yeah. His solution or his scientist's solution for lack of accuracy was multiple spears, basically.
Well, in a way, that was how, wars were fought with bows and arrows, the same sort of thing.
Yeah, because bows and arrows weren't all that accurate at over distance, but
that's right.
You fire enough of them, they're going to hit something.
Yeah, that's right.
That's an interesting story in itself, the history of bows and arrows and how the English defeated the French at Agincourt using the longbow, wasn't it? Is that the one?
So.
Yeah, and that was the end. That was the end of the knights era of medieval times because the knights became redundant. Their armour couldn't stop the longbow, as far as I understand it. Yes,
probably right.
Yeah, it's fascinating stuff, and love that question, Giles. But yes, in real terms, it's too easy to do what you suggest. It really is too easy, and I'm sure these kinds of ideas are bouncing around in the halls of secret buildings somewhere around the world. Anyway, thanks for the question. If you have questions for us, please go to our website. It is spacenutspodcast.com and spacenuts.io, the two URLs that we bought for $1.50. And you can send us your questions through the Ask Me Anything tab at the top. It says AMA. You go in there and you can send us text and audio questions. If you've got a device with a microphone, you're all set. Don't forget to tell us who you are and where you're from. We'd love to hear your voices, though. So audio questions most welcome. And while you're on the website, have a look around and don't forget to leave some reviews for us wherever you listen to us. And we appreciate that in advance. Thank you. And thank you, Fred. As always, we'll see you next time.
I hope we do. It's even if time is an illusion, it's still nice to go from one week to the next.
It is indeed. Yeah. All right. Thanks, Fred. See you soon.
Cheers.
Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio who was going to join us today, but we got nothing. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.